We have worked with linear inequalities for quite a while. With linear inequalities, the only difference, left out an E there, between ax plus b equals 0 and an inequality that's linear, like ax plus b, say, is less than 0, is that if we divide, or multiply, of course, but basically if we divide by a negative, we have to turn the sign around. We have to reverse the inequality sign. However, a polynomial or a rational is very, very different. If we have a situation like a times b is greater than 0, then either a and b are both positive, or a and b are both negative. We can't solve just one at a time the way we do when we take a quadratic and factor it and set it equal to 0. If we've got this times this is equal to 0, then let's call this ax plus b and cx plus d. How about? Then ax plus b equals 0 is sufficient. To make the whole thing 0. Because if this is 0, then 0 times this won't even matter. Or if cx plus d is 0, it will all be 0. However, in the case of, say, an inequality where it's greater than, if we've got something like this is greater than 0, we can't just set these greater than 0. If ax plus b is greater than 0, then at the same time, Cx plus D has to be greater than 0. Remember that greater than 0 means positive. For two things to multiply together and be positive, either they have to both be positive or they have to both be negative. You can't split this up into two separate, unrelated equations like you can over here. In order for it to equal 0, only one of them has to be 0. In order for the product to be positive, either they have to both be positive right then, or they have to both be negative right then. So this is a completely different situation, and we cannot do it the way we do just a linear. If you notice the way a quadratic is graphed, let's say we got a graph of a parabola like this. And say this is f of x. And I'm going to call this point A, and I'm going to call this B. F of x is equal to 0 at x equals A and x equals B. In other words, f of x means the y. So the y value is 0 at this point and this point. This is the point A, 0, and this is the point B, 0. F of x, the y values, are less than 0 for your x values between A and B, because for all of these points down here, for this point right here, for instance, this point has a negative y value. This point has a negative y value. This point has a negative y value. For every x from here to here, the y values are negative. So the y values are less than 0, negative, for A is less than x is less than B. For the x values between A and B, which we could also write as interval notation from A to B. This is the interval notation, not a point. And in this particular case, the y values are going to be positive, greater than 0, for x values that are to the left of A, or x values that are to the right of B. The interval notation would be from negative infinity to A, union B to infinity. So for this part of the graph, the y values are positive. For this part of the graph, the y values are negative. And for this part of the graph, the y values are positive. So it's dependent upon finding the points where it's on the x-axis. So we have to find, first thing we want to do is set it equal to 0 so that we can find the zeros. So we want to find the zeros of the function. Those are the x values that make the y equal 0. That gives us our x-intercepts. Because polynomials are going to be smooth, continuous graphs, they can't suddenly jump from being up above the x-axis to being below the x-axis without going through the x-axis. So these are the only places where the y values can change sign. If your y values up here are positive and your y values down here are negative, you know it had to have gone through the x-axis at some point. And the places where it goes through the x-axis are the only places where your consecutive y values can change from being positive to negative or from being negative to positive. So we find the zeros of the function, set it equal to 0, solve that equation, the equation. We want to mark the zeros on a number line. And then we want to find any x value in each interval to use as a test point. If we mark our zeros on a number line, and the zeros in this case, we were just calling A and B. So our intervals run from negative infinity to A, from A to B, and then from B to infinity. That basically takes the x-axis here and just translates it into just one line. And so we could find a test value here, let me call it T1, and a test value in here, I'm going to call it T2, and T3. Find the function values, the y values, for each test value. And mark, I got distracted, it's supposed to be and mark each interval as positive or negative. If f of T1 is greater than 0, in other words, if I plug this number into this function and I get a positive, I get something that's greater than 0, then the y values are positive for every x in that interval. If I plug in this number, T1, into this function, and I get a positive y value, because it's going to keep going this way. So I've got the point T1 and f of T1. If this number gives me a positive value, then it means every x value in here is going to give me a positive value. See what I'm saying? These are the only places that as I'm plugging in x values, that the y value could change from being positive to negative at the zeros. And so I'm using this as a test value to determine whether all the y values in this interval are going to be positive or negative. And a value in here is going to give me a negative for this particular graph, which means that every x value between a and b will give me a negative y. And if this value gives me a positive, that means that every x value above b is going to give me a positive y value.